Welcome back to Idea Mechanics. I'm your host, and today we're looking at how we can use TRIZ, the theory of inventive problem solving, to solve some of the most persistent bottlenecks in hardware design. If you want to see how we dismantle engineering challenges using a systematic toolkit, hit subscribe, ring the bell, and tell me in the comments which system we should look at next. For decades, consumer electronics have functioned as passive receptacles of power. They are brilliant, fast, and high resolution, but they rely entirely on us for their basic survival. We see this in the manual friction of everyday use. When a phone overheats, you have to turn it off. Step into a noisy street, you have to adjust the volume. If a single component fails, the device is useless until a technician intervenes. This is the user-managed trap, a sophisticated machine that still requires constant babysitting. But we can change that. We can build hardware that is responsible for its own health, performance, and operational life. Creating architectural autonomy means we move away from reactive troubleshooting and instead engineer devices with their own self-regulating nervous systems. High-performance microchips face a physical contradiction. Higher processing power creates intense thermal heat, degrading the battery or causing the hardware to fail permanently. To solve this, we look to TRIZ Principle 23, feedback. This involves building a mechanism that monitors the output of a system and uses that data to adjust how the system operates. In intelligent thermal management, internal sensors constantly pull processor heat, feeding a control loop. When temperature breaches a safe limit, the device reacts. It throttles clock speed and shuts down background processes to lower the thermal load. This adjustment happens in milliseconds, typically without the user ever noticing a drop in performance or a rise in temperature. These internal feedback loops allow the ecosystem to regulate its own safety, maintaining the highest possible performance while protecting the hardware from heat damage. While internal loops protect the hardware, devices also need to adapt to the environments where we actually use them. This creates another contradiction, a static audio output level competing against a chaotic background, like a quiet office suddenly becoming a noisy construction zone. Engineers apply feedback by using a microphone to monitor the environment. The device compares ambient noise, the spiking bottom wave, against its own audio output. As the environment gets louder, a control circuit adjusts the gain, stretching the audio wave to maintain consistent volume. Continuous external polling maintains this equilibrium, allowing the device to manage its own volume levels so the user doesn't have to. The most difficult challenge to a device's life is physical hardware failure. Normally, when a pathway on a circuit board burns out, the entire system stops working until it can be manually repaired. We address this with TRIZ Principle 25, self-service. This suggests designing a system to perform its own repair functions without external intervention. We achieve this through architectural redundancy. By building dormant pathways, the system monitors its own physical integrity. If a fault is detected, it automatically reroutes logic and power through a backup pathway, bypassing the damage to continue functioning. This is the highest form of autonomy. When a device executes its own maintenance and heals damage, it significantly extends its operational life. We often think of device intelligence in terms of processing speed or pixels, but a system's capacity for independent survival and adaptability adds a vital layer of modern reliability. Building resilient technology is not a matter of magic or high-level AI. It is a repeatable architectural skill that any engineering team can master. By deploying feedback and self-service, we turn abstract concepts of smart tech into practical, self-reliant hardware ecosystems. Thanks for joining me to explore these principles. I hope they help you build a culture of innovation in your own work. Keep engineering the future, my friends. Applying these structured rules allows us to build a layer of persistent reliability into the tech we use every day, ensuring our devices stay operational long after simpler designs would have failed.